In this video, I'm going to explain optimization. To understand optimization effectively, we will work through examples. This type of problems involve differentiation, so you need to know how to differentiate functions and find their derivatives. If you are not familiar with these concepts yet, I recommend you watching this introductory video before continuing. It covers the essential basics on differentiation that you'll need. Before starting with the problems, I would like to mention some of the uses of optimization in construction and the built environment. Optimization in construction is essential for improving project outcomes, reducing costs, enhancing sustainability, and ensuring safety. These are some examples where we can apply optimization: structural design, cost management, project scheduling, energy efficiency, environmental impact, safety and risk management. In an example of structural design, we can use optimization to ensure that the design of the structure is optimized for strength, stability, and safety, while using the least amount of material possible, which will reduce costs. Now we will start with the practical part. In this type of problems, the question will always be maximize or minimize something. So I think it's easy to identify when we need to apply optimization, therefore differentiation. When we optimize, we are trying to find the best option. Let's see this example. A rectangular garden is to be constructed. There is 18 meters of fencing available for the 4 sides of the garden. What should be the dimensions of the garden to maximize its area? We need to design a rectangle that has a perimeter of 18 meters. Before using differentiation, we are going to try to guess the option with the biggest area. The garden has a rectangular shape, and I need to find out the base and the height of this rectangle. The perimeter is 18 meters. For this first option, I'm going to decide that the base is going to be 6 meters. If the perimeter is 18 meters, the other 2 sides need to be 3 meters each. The area of this rectangle will be 6 times 3, 18 meters squared. I'm going to continue with a different rectangle with a shorter base. The perimeter is 18 meters, and now the base will be 5 meters. The length of the other 2 sides is going to be 4 meters, and the area of this rectangle is 5 times 4, which is 20 meters squared. I will continue with a different rectangle that has a shorter base. The perimeter is 18 meters, and now I have decided that the base is 4.5 meters. In this case, the other 2 sides need to be 4.5 meters. The area will be 4.5 times 4.5, which is 20.25 meters squared. So if I compare the area of these 3 rectangles, this one is going to have the biggest area. The rectangle with equal sides, which is a square. Before starting to solve the problem using differentiation, let's remember how to differentiate, how to find the derivative of a function. We have this function, y equals 5x cubed. There are 2 variables, y and x. If we want to find the derivative, we have to differentiate y with respect to x. And the way to do it is this: you times the power by the x and take away 1 from the power. 3 times 5 equals 15, x to the power of 3 minus 1, which is 2. In the problem that we are going to solve, we will have to do something similar. We need to differentiate a function. In this case, it will be a formula with respect to a variable. This rectangle has a base, b, and a height, h. In this type of problems, we need to ask 2 questions. The first one is, what do we need to maximize? We need to maximize the area of the rectangle. The formula of the area of the rectangle is base times height. We will need to differentiate the area, dA, with respect to a variable. But here we can see that we have two variables instead of one. The second question is, what is the constraint? The constraint is a restriction. It's a condition that the variables must satisfy. In this problem, the constraint is that the perimeter needs to be 18 meters. The perimeter of this rectangle will be the sum of all the sides, 2b plus 2h. And we know that the perimeter is 18. Thanks to the constraint, we will be able to express h in terms of b. 2b plus 2h equal 18. I'm going to rearrange this formula to isolate h. If I minus 2b on both parts of the equation, I will have 2h equal 18 minus 2b. If I divide by 2 both sides of the equation, I will have h equals 18 minus 2b over 2. And simplifying, this is 18 over 2, 9, minus 2 over 2, 1, which is b. So h equals 9 minus b. Now I can substitute h in the formula of the area. This equals b times h, which is 9 minus b. This equals 9b minus b squared. So now I have the area with only one variable. And now I will be able to differentiate a with respect to b. dA over dB equal, the power of b is 1 times 9 is 9, b to the power of 1 minus 1, which is 0. b to the power of 0 is 1, minus 2 times b, and b to the power of 2 minus 1, which is 1. I don't need to write it. To be able to calculate the maximum, I need to set this equal to 0. I have this equation and I need to rearrange it to find out the value of b. If I add 2b on both parts of the equation, I will have 9 equals 2b. If I divide by 2 both parts of the equation, b equals 9 over 2, which is 4.5. And now I will be able to calculate h. h equals 9 minus b, which is 4.5, and this is 4.5. The answer to maximize the area of this rectangle is when b is 4.5 meters and h is 4.5 meters, which is square, and it's the answer that we guessed previously. In the previous example, after calculating the derivative, I set it equal to 0. I'm going to show you why we have to do this. Here we have two curves. The minimum point on this curve is this. The slope at that point is 0. It's a horizontal line. The slope at the minimum point of the curve is 0. The maximum point on this curve is this. The slope at that point is 0. It's a horizontal line. The slope at the maximum point of the curve is 0. Remember that the derivative of a function is the slope. So if we want to find the maximum or minimum of a curve or a function, we just have to set it equal to 0. Now we are going to continue with a similar example, but in this case we won't be able to guess the answer. we need to use differentiation. A rectangular garden is to be constructed alongside a building. There is 30 meters of fencing available to include 3 sides of the garden. The building is acting as the 4th side. What should be the dimensions of the garden to maximize its area? When we have a problem of optimization, we need to find the answer for these 2 questions. The first one, what do we want to maximize? We want to maximize the area of the garden, the area of the rectangle. The formula of the area is base times height. What we want to maximize is what we will differentiate. We will differentiate A, the area, with respect to another variable. Here we have 2 variables, B and height. The second question is, what is the constraint? The constraint is a restriction, a condition that the variables must satisfy. The perimeter is 30 meters. And the formula of the perimeter will be 2 times B plus height. Because the 4th side is the building, so we don't need to consider this side. And we know that the perimeter is 30 meters. In the formula of the perimeter, I can rearrange it to make h the subject. If I minus 2b on both parts of the equation, h equals 30 minus 2b. And now I can substitute h in the formula of the area. So the area equals b times height. And the height is 30 minus 2b. This is 30b minus 2b squared. So now we have the formula with only one variable, which is b. We can differentiate the area with respect to b. To differentiate a function, we need to times and take away. Times the power of the variable by the variable and its coefficient, 1 times 30, times b to the power of 1 minus 1, which is 0. b to the power of 0 is 1. So 30 times 1 is 30. Minus 2 times 2, 4, times b to the power of 2 minus 1, 1. So we don't need to write the 1. To be able to find the maximum, we need to equal this to 0. So 30 minus 4b equals 0. If I minus 4b on both parts of the equation, 30 equals 4b. If I divide by 4 both parts of the equation, b equals 30 over 4. This is 15 over 2. This is 7.5. Now I can calculate height. So height equals 30 minus 2b. 30 minus 2 times 7.5. So height is 30 minus 15, and this is 15. The dimensions to maximize the area of the garden are 7.5 and 15. This is another example. A cylindrical tank needs to hold 100 meters cubed of liquid. To minimize the amount of material used, what should be its dimensions? We need to start with the 2 questions that we need to ask in every optimization problem. What do we want to minimize? We want to minimize the surface area of the cylinder. So we need to calculate the formula of the surface area of the cylinder. To be able to calculate it, we need to know the area and the perimeter of a circle. The surface area of the cylinder will be the sum of the area of the base, pi r squared, plus the area of the top, pi r squared, plus the area of the vertical surface, which will be the perimeter of the circle, 2 pi r, times the height. So the total is 2 pi r squared plus 2 pi r h. The second question is, what is the constraint? The constraint is the restriction. The constraint is the volume, which is 100 meters cubed. The formula of the volume is the area of the base pi r squared times the height, h. So the volume of the cylinder is pi r squared h, and we know that this equals 100. We need to make h the subject in this formula. If I divide by pi r squared both sides of the equation, h is 100 over pi r squared. And now I can substitute h in this formula. So the surface area is 2 pi r squared plus 2 pi r times h, which is 100 over pi r squared. This pi and this pi are cancelled. This squared is cancelled with this r. So the surface area is 2 pi r squared plus 200 divided by r. Before calculating the derivative of this formula, I need to change this term using this law of indices. So this is 2 pi r squared plus 200 times r to the power of minus 1. And now I can start differentiating the surface area with respect to r. I need to times and take away. I need to times the power by r and its coefficient. So 2 times 2 is 4 pi r to the power of 2 minus 1, 1, minus 1 times 200, which is minus 200, r to the power of minus 1, which is minus 2. So this is the derivative, and I need to equal to 0 to be able to find the minimum. I will need to apply again the same law of indices to this term. 4 pi r minus 200 over r squared equals 0. So 4 pi r equals 200 over r squared. Now I'm going to continue rearranging. If I times by r squared both sides of the equation, I have 4 pi r cubed equal 200. R cubed equal 200 over 4 pi. And this is 50 over pi. R is the cube root of 50 over pi. This is the cube root of 15.92. So R is 2.51 meters. Now I can calculate h. H equals 100 divided by 2.51 squared times pi. And this is 5.03 meters. So the cylinder with the minimum surface area is the one that has a height of 5.03 meters and a radius of 2.51 meters. I will finish with this problem, which is an exam question. It's very similar to the previous one. To reduce the effects of hydrological conditions, a water retention pond will be excavated in the field. The retention pond will be cylindrical in design, have vertically excavated sides, and will need to have a volume of 200 meters cubed. To reduce the amount of space taken by the pond, both depth and radius need to be kept to a minimum. Calculate the minimum radius of the pond to achieve the required volume. Give your answer to 1 decimal place. This is an optimization problem because they are asking for a minimum, the minimum radius. We will have to use differentiation. We need to start with the two questions. The first one, what do we need to minimize? We want to minimize the surface area of the cylinder because both radius and depth need to be kept to a minimum, and both are part of the formula of the surface area. To calculate it, we need to know the area and the perimeter of a circle. In this case, We are not going to consider the area of the top because this cylinder has no lid. To calculate the surface area of the cylinder, we need to add the area of the base, pi r squared, plus the area of the vertical surface, which will be the perimeter of the circle, 2 pi r times the height. And this is pi r squared plus 2 pi r h. The second question is, what is the constraint, what is the restriction? And the restriction is that the volume needs to be 200 meters cubed. To calculate the volume of the cylinder, we need to times the area of the base, pi r squared, times the height. So the volume is pi r squared times height, and we know that this is 200. We know that we have to differentiate the surface area because this is what we have to minimize. In this formula, there are two variables, r, the radius, and h, the height. Thanks to the constraint, we know that h equals 200 over pi r squared. And we can substitute h in the formula of the surface area. So the surface area is pi r squared plus 2 pi r times h, and now we know that h is 200 over pi r squared. Pi and pi are cancelled, r and the square are cancelled. So this equals pi r squared plus 400 over r. To be able to differentiate this term, we need to apply this law of indices. So the surface area is pi r squared plus 400 r to the power of minus 1. And now we can find the derivative. If I differentiate the surface area with respect to the radius, I need to times and take away 1 times the power by r and its coefficient, so 2 times pi r to the power of 2 minus 1, which is 1, minus 1 times 400, which is minus 400, times r to the power of minus 1, which is minus 2. And we need to equal this to 0 to be able to find the minimum. We need to apply again the law of indices to this term. So 2 pi r minus 400 over r squared equal 0. 2 pi r equal 400 over r squared. If I times r squared both sides of the equation, 2 pi r cubed equal 400. If I divide by 2 pi both sides of the equation, r cubed equals 400 over 2 pi. And this is 200 over pi. So r is the cube root of 200 over pi. The radius is the cube root of 63.66. So the radius is 3.99. We need to round the answer to 1 decimal place. So the answer is going to be 4 meters. The pond with the minimum surface area is going to have a radius of 4 meters.